Chapter 14, Electromagnetism. I'm just gonna give you a quick overview of Chapter 14. This is actually the foundation of alternating current. So we're just gonna be talking a little bit about Chapter 14. So the first thing I want to talk to you about is what we call the amp turns of magnetic force. So 14-1, magnetic motive force, MMF. So we know that if we add more current, what would happen? Well, we add more current to a coil. So if we have a coil right here, let's say we have a coil right here. Let's build ourselves a coil. And I might have to break this lecture up just a little bit, but we'll take it one step at a time here. So if I keep doing this, and might break it up. So we'll talk about that in a minute. So if I actually take this, and I bring this over, and I take a battery, and bada boom, there we go. And I put 30 volts right here. There's my 30 volts. So first thing is, if we take and if we increase, that's increase the number of turns, we get stronger magnetic field. So a stronger magnetic field. So we get a stronger magnetic field. Also, what we can do is more, like I said, more turns. But if we have more current, if we increase the current, we get a stronger magnetic field. Well, how do we increase the current? Well, if we want to increase the current, the only way to increase the current, well, we would have to increase our voltage. So if we increase the voltage here, we get more current equals a stronger magnetic field. So when we talk about this, we call this the amp turns. And the equation for that is I times N, and that's measured in MMF. All right, MMF. So what is MMF? This is the magnetic motive force. Pretty straightforward, okay? So basically what the units for this is magnetic motive force, is to get this as current times N. So an example of this would be if we have I is equal to 5 amps, and our number of turns is equal to, let's say N is equal to 100. So we use the equation. So I'm going to abbreviate AT, amp turns, is equal to I times N. So in this case, we're going to take I is 5 amps. You notice I'm using my units. And N is 100 turns. I'm going to keep that alone. So that gives us 500 MMF. Okay. So that's pretty straightforward. So basically this is, with this current 5 amps and 100 turns, it could be a strong magnetic field, it can be a mild magnetic field, depends. So we can test this. We can actually test this, and we can actually get, we can set up a voltmeter, power supply. So we increase the voltage till we get 5 amps, and then we have number of turns as 100. And what we do is we should be able to measure that the strength of the magnetic field. Okay. So when we look at the current itself, we know that what's going to affect current. So if we want to increase current, well, all wire, so I is in amps. Let's do that. And we know that a wire has resistance. Okay? We know it has some resistance. So we can say that if we increase the number of turns in the wire, what technically we're doing is increasing the resistance of the wire, which in turn will increase the current. That's what it's basically saying. Okay. So we have to keep in mind that as we increase the number of turns, now we're increasing the resistance of that coil itself, that solenoid. It's called a solenoid. We'll get into the definition of a solenoid. But we're also increasing the magnetic field, which is great. But the problem is we actually are heating up, and we get a lot of power loss. We can actually have a lot of power loss in this. So to keep that in mind. So let me talk a little bit about that again with the current. So again, well, how do we know how much resistance in a wire? What can we do how we can find the resistance of the solenoid in the wire? So what we could do is take a multimeter, set it to ohms, and then we can measure the resistance of the wire. We should see, if it has a lot of turns, and we should see a high value of ohms, not anything really like above 10, but we should be able to see it above 1. So it could go up a little higher depending how many turns. If we have 10,000 or something turns, you're going to expect a lot of resistance to be through that wire. Just remember, you can actually figure this out. You can actually figure, if you take a spool of wire, such as electrical wire, or 500 feet of electrical wire, and you have one end, and you strip off the bare copper and the other end bare copper, and you put a multimeter, an ohm meter to it, set it to ohms, voila, you could figure out that you actually have quite a bit of resistance on it. You can actually compare those measurements. So in the book, it does talk about this in 14-4. I is equal to VOR, where you're looking for the current. Remember that our MMF, which is our units for, is I times N. So we have 2 amps times 2, let's say 250 turns. So let's say we have current 2 amps and we have 250 turns. That gives us 500 amp turns. So that's the answer. That's pretty much it. And they do talk about the Gilbert. That is so basically a 1 amp turn equals 1.26 Gilbert. So that's just some of the equations. We're not going to get into that too much because we're not designing things. But the biggest objective we wanted to get understanding on this part was the number of turns. So if you ever have to build a coil, or you have to repair a coil, or you have to rebuild a coil, these are the type of things you have to take into account. You just can't just put everything together and hope for it to work. So remember, you have to take into account of all the specifications of the coil. Is to measure the ability of material to support the formation of a magnetic field, and the equation for permeability, which is, you have that, it looks like a mu, it is a micro, but it's actually mu, is equal to B, its symbol is B times the flux density, and that's in Webers per square meter. So mu is equal to B over H. So look at that in the book, and you should be able to get some information on that yourself. Magnetic hysteresis. This is the magnetic field that's applied to a ferromagnetic and dipoles of line. So a magnetic hysteresis is a magnetic field is applied to a ferromagnetic. Remember, ferromagnetics are materials that we normally use, such as iron, and the dipoles of line. Even when the field is removed, the magnetic field is still present. So that's what magnetic hysteresis means. So when we create a magnetic field, we are creating it using a ferromagnetic material. But when we actually, after we create the magnetic field and remove the power, we're actually getting a field, and this field is going to stay there even after we remove power. Hysteresis loss is when magnetic forces change thousands of millions of times per second, and this can cause a loss of energy. So basically, what we're talking about here is under hysteresis loss is that an alternating current. When we actually are creating an alternating current, we're actually changing the magnetic field north south north south. When you do it millions of times, we're actually causing hysteresis loss. The solution to this, the solution to removing hysteresis loss is slowing down the number of times we're doing it. So instead of going from 60 hertz, we go to 50. Hence why, maybe why they use that in Europe. So demagnetization. This is disalign the domains of a magnet. This is actually to collapse, reduce, remove the magnetism. And we actually give a name to this. We'll get you in a second here. We do this using alternating current. And a good example of this we want to do is erase information on a magnetic hard drive, because the hard drives are magnetic. And what we'll do is actually we'll create alternating current, and then what happens is that through the process of applying this alternating current back and forth, which actually we're doing is degaussing this thing. And you might have heard of the word degaussing. So degaussing is actually removing the magnetism on it. It's basically there's no magnetism anymore, and you erase it. We do this on hard drives when we don't want anybody to know it. So when we talk about a magnetic field from electromagnet, we have to know which direction the current is going, and we can usually use the left-hand rule. The left-hand rule basically is what we do is we grab the conductor itself, and we actually take our fingers and it points in the direction of way we're winding. The thumb will point in the direction of the current. So basically, if your thumb's pointing toward the top, that means you actually have the north pole on the top. If it's pointing to the bottom, that is the north pole. So basically, the left-hand rule is a way for you to actually determine which direction the magnetic field is going and which of the north and south poles. When we talk about fields aiding and fields canceling, we're taking magnetic fields and we're aiding and we're increasing it. So this is becoming stronger. When we say fields canceling, this is opposing it. So this is when we're actually canceling it out. So a solenoid. A solenoid is a coil of wire with more than one turn. That's the definition of a solenoid. So an ideal solenoid, its length is greater than its diameter. So keep that in mind. A solenoid concentrates the magnetic field inside the coil and creates two poles. So what we're doing is creating electromagnetic. We see these solenoids all the time. We use them in relays, we use them in starters and cars are two examples. So the more turns, the stronger the field. We use left-hand rule to determine the poles. Again, same thing. Motors. So basically the motor is a pretty straightforward piece of equipment, but it doesn't really have any moving parts besides the bearing, okay? But it really doesn't. So basically what we're doing on a motor, we're actually creating a physical motion from force of a magnetic field. So what happens when two magnetic fields in the same polarity hit each other? They repel. So if we repel something, what's going to happen is we'll get some twisting motion, and that's called torque, the effects of force in producing rotation. So basically what we're doing on a motor is we're creating a magnetic field, and it's an alternating magnetic field. So what we can actually do is we can use AC or we could use DC. So on an AC motor, we're just creating a magnetic field. Again, we use coils of wire and we wrap it around. When we have a current induced there, we create a magnetic field. When we alternate that field and north to north and south to south line, we actually start causing the turns. We cause the motor to turn, the rotor to turn. So what's interesting about this is that on a single-phase motor, it takes a little bit of a push to get it going. Sometimes we would use the old ways, we'd just give it a little twist by the hand, and the new ways we actually use capacitor to actually get that motion going. And that capacitor actually creates a virtual, let's call it a virtual AC sine wave, so a virtual voltage. So, like I said, torque, the effective force in producing the rotation. Now, I messed up here. Let's go back to the AC. If three-phase AC, we have three poles. So on a single pole motor, we only have one, it's 120 degrees. Think about this. How many degrees are in an inner circle? 360. So if we have only 120 degrees, well, it's really hard for that motor to turn by itself. So hence the fact why we use capacitor. So if we go ahead and now increase it to 220 volts, now we have actually two poles which we use. We don't call it two-phase. We call it. I'll give it to you as two poles. So now we have two things. So now we have 240, 120, 120. Now we have, if we put it at the opposite end of each other, now what happens is we get some torque that can actually be created. We don't have to do any of the turning by a capacitor or by hand. A three-phase is actually the most ideal motor, more expensive. Now they're 120 degrees apart. So 120 degrees apart times it by 3 gives you 360. So you see that it's more and more efficient. Now, I think I just messed up on the single-phase 220. 220, we look at it, take 360 divided by 220 by 2, it gives you 180, not what I said, so my mistake on that. So, Lenz's law. This is used to determine the direction of induced voltage or current. Basically, when we start looking at this, we're going to get into eddy currents, and that's waste of energy. But the direction of the induced current must be such that its own magnetic field will oppose the action that produces the induced current. So I'll talk to you a little more about that during lecture. But basically, Lenz's law is used to determine the direction of induced voltage or current. I want you guys to read this chapter 14 to understand it. I will talk to you briefly about it, but at least my notes will be on there, and I'm going to clean them up just a little bit, but at least you'll have an idea of what's being chapter 14 is about. Thank you, and I look forward to seeing you soon.